Okay, so today's lecture we're going to do, this is actually going to be our last conversions test. There are two of them, but the main one is going to be the ratio test. I'm going to spend most of the time on that one. All right, so let's start right away perhaps with how this test works. It's sometimes easier to just start with what we need to do. So we have a series, and it could be any series now. And so this is why the ratio test is very useful. It can be used on negative series with negative elements and so on. And so what it is that we do, so say again from 1 to infinity, but sometimes it could be 0, right? So remember, we are flexible there. Okay, so what you need to do, and the ratio, the word ratio comes from the fact that it's the following limit. So it's again a limit that we're going to calculate, but this time it's this limit. And I'll explain what this means. So an is the formula that of your series. What is an plus 1? Well, it's the same formula where you place n by n plus 1. Okay? And then what is now, you calculate this limit. And this limit, well, if it exists, let's call it rho. Rho, this is a Greek letter r. You can also write r if you rather do. And there are 3 possibilities. Either rho is less than 1. That's the good case, convergence. Or rho is bigger than 1. That includes, of course, also infinity, or even that the limit doesn't exist. So if that is the case, we have divergence. So what's missing? The case equal to 1. What's happening then? We don't know. So the fancy word is inconclusive. So be careful. So when you get this, if you would get a limit that's equal to 1, that means you were using the wrong test. The ratio test is not the correct test for this particular series. Hopefully you don't get into this situation, but it could always happen. But it's best to see this work at using some examples. I'm going to start with an easy example. So here is one. Let's look at the convergence of this series. And at the same time, I already pointed out why this ratio test is very useful here, because if I would look at this series, up to the test that we have seen up to now, none of them really work. You cannot integrate. If you think about this, it's going to be very difficult to integrate. You could actually. It's not really true what I say here. You could integrate using integration by parts, but it's tricky. It's not an alternating series, so that wouldn't work. And what is the other test that we have? Limit comparison test. The problem is, okay, the top is a polynomial, the bottom is an exponential, so it's the mixed form of p series and geometric series. So mixed forms, therefore, are something that we cannot treat, and this ratio test is really very good for that. So let's see how it works. Okay. So what we have to do is calculate this limit. And the first important step is to get the limit correctly, write it down correctly. So it's the limit for n going to infinity. Now, also notice there are these 2 bars here, they're not for nothing there, there's absolute values. Now, in case this doesn't apply here because everything is positive, but later you'll see we'll often use this when there are negative things, or possibly negative things. Okay, so, and it's a fraction, so absolute value of a fraction. What's the fraction? In the bottom, you get your an, that is this guy. So you write this in the bottom. And now comes the trick. In the top, you have to write the same formula, but replace everywhere n by n plus 1. Okay, I'll do this. So this would be just n, and now let's replace n by n plus 1. So this would be, do it in red, n plus 1, and the same here. This would be n plus 1. So this is what we need to calculate. Now we have a fraction divided by a fraction. We know what to do this. Simplify the fraction by flipping this one over, right? Bring it up by taking the reciprocal. Okay, so it's the limit for n going to infinity. We have this n plus 1. Everything is absolute values. We don't need to write the absolute values anymore because everything is positive. So this is the fraction, and the flipped over fraction is this one. You agree with me? Okay. Now, it's actually better to organize these things a little bit more, group them together, meaning these two are powers of 2, so let's group them together. And then these two are the polynomials, so group them together. Why do I do this? Well, in particular here for these guys, you know how to deal with fractions of powers with the same base. Namely, you just subtract the exponents, right? You can write it in the bottom, in the top. Since the bottom is the biggest exponent, I'm going to write it in the bottom. So what I have is, what I'm trying to say is, in other words, if this cancels and I have a 2 left. I hope you see that, right? Because you have the exponent n plus 1 minus n, which is 1. All right? That's why I get the 2 here in the bottom. Now this one I cannot really cancel out. Be careful. Well, I can, but you have to, if you cancel, you have to cancel both terms. Very important. So let's do this. In this case, it actually works very easily. So I get limit for n going to infinity. So this was 1 over 2, right? There was 1 on top and 2 in the bottom. And then this one was 1 plus 1 over n. Okay, and what happens if I put in infinity now? Now everything works nice because this will go to 0. And therefore the limit is a half times 1, in other words a half. So this is the row. The row that we were talking about is this in this boxed formula here. And so let's look at the condition. Less than 1, that's the case we're in now, right? Row is less than a half. So we get convergence. That's it. Okay. Well, I said step 1, that was actually really one step. But what I meant to say is here, somehow the most important part is to get this, the right thing, the right limit. And then the rest is calculating limits in various ways. Obviously, this is also sometimes going to imply to do L'Hopital and stuff like that. Okay, let me give you, let's do another example. Yeah, I'll do quickly another example to show you that you don't always get nice things. Well, I want to give an example where you have not convergence. So let's do this one. Okay. Okay, so the ratio test, what we have to do is calculate the limit of this ratio. The ratio consisting of the element and the next one in the series. Okay, so what is it in this case? Okay, in the bottom, everything is positive, so I'm not going to write the absolute values anymore. Is this guy. And now make sure, try yourself before you go on, what is in the top? Okay, pause the movie and think about it. What is in the top? Write it up and then check whether it is the same thing. I'll do it in red. The n becomes n plus 1. The 5 to the power n becomes 5 to the power n plus 1. And the 3 to the n becomes 3 to the power n plus 1. Okay, now we have a sum here, so it's safer to write everything always between parentheses. Good. And then this fraction we're gonna simplify first by multiplying. Let's see what's in the top. So the n plus 1 and the 5n plus 1, right? These are these guys here in the top. And then since we flip over the bottom, this will now go in the top. I hope you see this. If you don't see it, do an extra step here. And what goes in the bottom? Well, this guy is in the bottom. And it's a power of 3, so I'm going to write it here. And then also these two guys. So you see how I align them? Because a lot of calculations now happen, right? So again, if I scratch out these two guys here, what in left is 5 in top, right? Because now the highest power is in the top. This one, I would get a 3 in the bottom. And then this one, I can do the division. But perhaps what we normally, this might be a little bit harder, a bit more complicated thing. So let me show you what you don't normally do in these cases. Well, we have 5/3 and then we have n plus 1 divided by n. And what we do is divide by the highest degree term. That's how we deal with these limits of these kind of rational functions. Which of course in this case is just n, which is really just dividing top and bottom by n. So we get this 1 plus 1 over n. And as before, if I plug in infinity now, then this will be 0. And so what I get, okay, 5/3. which is bigger than 1, and therefore we have divergence. Okay? Let me give you one example where you actually run into problems. So suppose we have this one here. Okay? We do the ratio test again. So this is, I'm always doing the ratio test, I'm not writing it up. And n plus 1, that's what we need to do, but the formula is not important. It's to fill it in correctly. Okay, in the bottom we get ln over n, and again, especially if you were not getting it right the first time, halt the movie and look at what the solution is. This n has to be replaced by n plus 1, and since it's a sum again, I put parentheses around it. Okay, and then the bottom becomes n plus 1. Okay, so this is the limit for n going to infinity. Let's ln plus 1 goes in the numerator. I hope you see that also this n goes into the numerator, and in the denominator we get this n plus 1 here, this one, and then the ln of n as well. Good. But now getting a bit of a problem. We can remember in limits, one thing you can do is you can split limits. Limits are very nice, you can do almost everything with them, so we could do this. We can try to calculate this limit, and also this limit, and then multiply. Right? Calculate each of these limits separately. Why do I do this? Because in this one, we have now done it several times. What you do is divide top and bottom by the highest degree, so let me quickly do that. So the highest degree here would be n, right? So divide by n, divide by n, divide by n. Now what do we do for this one? This is not highest degree thing, we cannot use that. So here we have, if we plug in infinity, so you guess it, L'Hopital. Right, okay, so if I do L'Hopital for this one, then actually I should do, I do the intermediate step, right? Replace n by x, to make it a function. So this is an x, right? So a function now. And then as we already noticed, this one here, this would be, let me write it up, what is left here after I do the calculations, 1 plus 1 over n, and then we know that this last 1 over n here, it goes to 0. So this whole thing is just 1. Okay, so it's not really something that we have to worry about, but now about this one, here I'm going to do the L'Hopital, and that means I have to take derivatives. So that means 1 over x plus 1 divided by 1 over x. Correct? Okay. And if I plug in infinity, well, I get 0 over 0, so I should perhaps better simplify this fraction again. This would be an x over x plus 1, right? You see how it goes? This one will go up because we take reciprocals. Okay. Now, this is again of the previous form. Divide top and bottom by the highest degree, which is an x again. So we divide by x, we divide by x, we divide by x, we get limit for x going to infinity, 1 over 1 plus 1 over x. So this goes to 0. So 1. Okay, because this was already 1, right? And now we have this part is also 1. The whole thing is 1. Now that's unfortunately not good, because this is now here. And this means inconclusive. Meaning, we don't know yet. It might well be that this function is, that the series is increasing, or it might is convergent, or it might be divergent. We actually really don't know yet. And therefore we need to use a different method. And I leave it as a homework. It actually is one of the exercises we did already to figure out what it is. I'll give you the hint in the rule test. Okay, and I'll give you the answer so that you can check. I think, yes, I'm pretty sure that this is going to be divergent. Okay, let me think a little bit about it. Why am I saying, is this true? Yes, of course, yes. Okay, all right. So, but now comes a very special type that we're gonna run into a lot, and I have to discuss. And here's another example. Suppose we have something like this. Let me do this one first. Now we have come already across these n factorials, right? Remember, n factorial was 1 times 2 times 3 times 4 and so on, all the way until you get to n, whatever n is. Okay, remember that, right? So this is kind of a complicated number, and it actually, these numbers become very big. 10 factorial is already a huge number. And worse of it, it's not a function. X factorial does not exist. So you cannot even do anything like L'Hopital or any of these things, because as a function of a real variable, you cannot sketch the graph of this function. There's no graph. This is not a function. So we only can talk about n factorials. Now that's not important. So let me get rid of this. This is not something that we're going to have to bother about. But the point was, I cannot not even think of doing integral test here because it's not even a function. Okay, now when you have factorials, that's a big rule, factorials almost always, well, I don't think I've seen another case where it's not, you're going to have to do the ratio test. Why? Well, let's calculate out and see what we need to do. So we have to calculate this limit. I'll write it up one more time so that you get used to the formula. Okay, and what does this mean in this case? Okay, in this case, again, everything is positive, so I'm not going to do the positive. I'll do something with a negative later. So we have n factorial over 2 to the power n. Now in the top, remember, replace n by n factorial. So I'll do it one more time in slow motion if you want. So I'm going to replace this n. Oops, that was a bit too much. But so by n plus 1. So we get n plus 1 factorial. But again, it's a sum, much safer to put a parenthesis around it. I mean, I say much safer, you have to. Okay? And then same here for this other n. I do this one here, that becomes n plus 1. And of course, I had accidentally erased my fraction. Good. Okay, we do the flipping over part. So we get the n plus 1 factorial on top, and also this 2 to the n will come on top. And then in the bottom we have the n factorial, I'm grouping them together, and the 2n plus 1. Let's do the easy one first. The easy one is the powers of n here. The powers of 2, sorry. So, and what we left is a single power of 2 here. Now what about this guy here? And this is a trick. Once you understand the trick, it's actually very easy, but you have to understand it. And so let's go, what is n plus 1 factorial? Well, let me write it up here. Well, it's 1 times 2 times 3 times dot, 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 all the way up to n plus 1, right? It's a bit further that we go. How much further? Well, exactly one step further, right? So there's one extra factor. So what's the previous factor? Would be n here, all right? Look, this is the same as this. So another way of saying this is, let me give myself a bit of space here, is that we actually have this. This part here, I'll take a different color. The green part, that is actually n factorial. And then the red part is just one extra factor, n plus 1. So what I'm saying is that, I'll write it here, this n plus 1 factorial can be split, can be broken down in two factors, n factorial and n plus 1. Now let's try to do this exactly there. Okay, so I get limit for n going to infinity. So the n plus factorial can be written as n factorial times n plus 1, right? That's exactly what I said here. Right? n plus 1 factorial is you go all the way up to n, and then you have to go one more factor, that's n plus 1. And now in the bottom of n factorial, I see two things that I can scratch out, because now they're products, and so I can cancel them. So this cancels with that, and I have an n plus 1 left. Okay, and so what I'm left with, so we have n plus 1, and we have this 2 here, so this is what we're left with. And this would be infinite, right, the limit. So unfortunately, that means that this guy is not convergent. So this would be divergent. This is one of the strong cases where this fails, right? Here are where we are in this case now. Infinity is bigger than 1. Okay. So the whole thing is I'm understanding really how these factorials work. Okay, I'll do a couple of more. Let's do something with an alternating guy. Why not? I want to do n squared 2 to the power n over n plus 1 factorial. Okay, let's try this one. It's a little bit more work, so stop the movie, try to work it out for yourself, and then look at the solution. Alright, so we take the limit. in the bottom we have n squared 2 to the n plus 1 factorial. So what we have in the top, again, everything is positive. Well, no, that's not really true. There's a negative sign here. So taking absolute values means that I'm going to ignore that negative sign. So let me write it up perhaps. So we would have a minus 1 to the n here, right? But then absolute values tells me that I can get away with this negative sign. Because this minus 1 to the n is either minus 1 or 1. And if I take the absolute values, it's always 1. So that's why I don't write it. So it's easier just to get not too overloaded. I'm going to only do the positive part. Okay, you understand why I ignored the minus 1 to the n? Okay. So then on top, what do I get? Oh, I got myself a little bit squeezed in here. Okay, I'm going to write it small. Sorry. So what I have here, well, let me do it over because otherwise it's actually important to see really what is going on here because it's a little bit more complicated. Okay, so limit for n going to infinity. We said in the bottom we had n squared 2 to the power n plus 1 factorial. Let's do it again. I'm going to write first the original and then replace it by, so this is not correct, right? Now I have to replace n by n plus 1. So n I'm going to replace by n plus 1 in here. So let's do this one by one. I'll try to do this with my eraser here, but hopefully I don't erase too much. Okay, so yeah, so this will be n plus 1. That was easy. The other one we also have done before, so that should be also not so hard. So this is again n plus 1. But now what here? Well, I have to replace by n plus 1. Let's just do this. Let's follow the rules. It's simple. That's what mathematics is. Always follow the rules. N plus 1. What does it mean? N plus 1 plus 1. That's n plus 2 factorial, right? So let me rewrite this now. So what we have is the limit for n going to infinity. On top we have an n plus 1 squared. We have a 2 to the power n plus 1. Also this guy will come on top. N plus 1 factorial. And in the bottom we have, well, this as we said was n plus 2 factorial, correct? And then we had these two guys also in the bottom, so the 2n and the n factorial. Oh, right, no, sorry, yes, n squared. Yeah, but I should, as I was saying before, I should align them, right? So let's align them already. So I should have put this n plus 2. Okay, so the n squared should have come here, and the n plus 2, this guy should have come here. I don't want to write it again, so I'm doing this now. Good. The easiest one is always these powers here, because they cancel out and have a power 2 left. Okay. Now, also rather easy once you understand this trick here is that you can rewrite a factorial as a smaller factorial. Let's look, where is the biggest? The biggest factorial is here. And so I should write that bigger factorial now in as a smaller factorial, in terms of the smaller one. What is this in this case? Look, okay, limit n going to infinity. The n plus 1 squared over n. There's one way I could do is actually put it as one symbol. So I could put this as a single square, because now inside again it's the simple. I hope everybody sees that this limit is going to be 1 inside. But that's not the issue here. Let's focus on this part here. So I'm going to rewrite the bottom in terms of the top, in terms of the smaller factorial. So n plus 1 factorial, what does that do? It goes from 1 all the way to n plus 1. Do I have to be there? No, I have to go to n plus 2. So I need an extra factor, namely n plus 2. That's the one that's missing. All right. And in the top, it's just n1 plus factorial. And now you see, there we go. Whoop, whoop, gone. Okay, so we already noticed also that we're here going to divide by n, divide by n, divide by n. So we calculate this limit separately. So let's see what we all have now after all this trickery. So we get limit n going to infinity. We have 1 plus 1 over n over 1. Well, I should perhaps even write the 1. Let me don't write this anymore. Well, I'll leave it. And then square. And then here we have a 1 over n plus 2. Now, if I plug in infinity, then this guy is 0. Okay, what happened to my red? Then this guy is 0. So this is only 1 squared. And this, of course, is 1 over infinity, which is 0. Is that good? Our limit should not be 0. Well, no, in this case it's very good, because in this case the condition, that's why you have to get used to all these tests. They all have different descriptions, right? And here the conditions. Here the condition is less than 1 is the good case. Okay, so I can write here less than 1, so we get convergence. But by the way, since I had to take the absolute values here, what I actually proved was that not only that the series is convergent, but can you say absolutely convergent, right? Because even if I ignore the negative sign, it would be still the same calculation. In fact, I did ignore the negative sign. And so the series would actually give me absolute convergence. So ratio test is ideal for also absolute convergence. Okay. I'm going to do one more that's a little bit going to be trickier, but you're going to have to deal with this. So here's one, limit for n going to infinity. I'm going to do n factorial, 2n factorial. Okay, so again, add it up. N factorial times n factorial over 2n factorial. Again, everything is positive, so I'm not writing absolute value signs anymore. So again, I'm going to do this one more time, replace each of them by n plus 1, each n, right? So, okay, the first one, that will be an n plus 1, n plus 1, in parentheses, because it's a sum. The second one, well, it's the same thing, right? Hello, what happened? For some reason, it doesn't raise. Okay. N plus 1. But now what about the last one? Okay, let's place this n by n plus 1. That's how you do it, right? But be careful. So what is the result here? Let's read this out. What does it become? This is going to become, I'll write it here already. Okay, let's put everything in there. The n plus 1 factorial goes on top. The n plus 1 factorial goes on top. Now they actually match with these n factorials here in the bottom. And then this guy, because it's in the denominator, in the denominator becomes the numerator, right? So this is 2n factorial. What is this now? Notice that it is, you might have thought it's 2n plus 1. No, it's 2n plus 2 factorial. Right? Work this out. 2 times n plus 1 is 2n plus 2. So be very careful. I said replace n by n plus 1. That means that 2n is replaced by 2n plus 2, not by 2n plus 1. All right. Now, let's rewrite everything. These are reciprocal, factorial, so we can rewrite them. We have already done this several times. This is now n factorial times n plus 1. One further, to get from here to there, you have to go by one more factor. Okay. The same for the second one, of course. And then this is now the bigger one. So it's this one I want to replace in terms of 2n factorial. So, okay, let's write here. Let's first copy these two guys before I forget. N factorial and factorial. No. Now what about this guy? So I want to write it as 2n factorial, right? This in terms of the lower one. And so what am I missing? Remember, it's the product from 1 all the way up to 2n plus 2. So, and 2n factorial is from 1 all the way up to 2n. So what is the next one? N plus 1. 2n plus 1. That's the next one, right? But am I there? No, because you have to go to 2n plus 2. So you have to go another factor, 2n plus 2 here. Okay? So that's perhaps something that you have to get a little bit used to. If you really think about it, this is really what happens, right? If I go from here to there, what more do I have to do? Well, you have to go from 2n to 2n plus 2 in 2 steps. 2n plus 1, 2n plus 2. That's why you get these two factors here. And now everything can be, again, scratched out. This with that with this, and this with that. Okay, so what I'm left with, let's do it in black again. It's the limit for n going to infinity. N plus 1 times n plus 1. And in the bottom I get 2n plus 1 times 2n plus 2. Actually, you can factor out the 2. And it's nice because now I can cancel one of the n plus 1s, right? And if this one, how do we do this one? It's always the same, right? It's a rational function divided by the highest degree term, which is an n here. So divide everything by n, oops, not there. Divide by n and divide by n. So I'm left with the limit for n going to infinity, 1 plus 1 over n, right? And in the bottom I have 2 plus 1 over n. So this will go to 0, this will go to 0, and therefore what I'm left with is a half, which is less than 1. That's good, that means convergence. Okay, so that's the ratio test, and I'll give more examples, and then we'll do a test a little bit later on the ratio test, a quiz I mean. And but the title also was talking about this guy, root test. Now I'm going to go very briefly over that, because although the book kind of deals a little bit more about it. By the way, the book also explains why the ratio test works and so please read a little bit more for more background information. But the root test is something that rarely we will use, but I need to discuss it anyway, and sometimes it could be useful. And it is kind of similar, and that's why it's in the same chapter, I guess, as the ratio test. Namely, it's a certain limit that you have to calculate, and then this part is going to be the same. But what's the limit here? And so what we're going to calculate is, what we're going to calculate, instead of a ratio, a root. What root are we talking about? So, okay, here, I'll write it up. Let's start from 0 for not always having to write the same thing. The root test. So in the root test, I'm going to calculate rho. This is again the limit, a limit that I'm going to calculate. And this time, I'm not going to take the ratio of the an's, I'm going to take the nth root. So the same n as this n here. So these are the same things, okay? And then, as I said, the conditions are going to be the same. If this is less than 1, then we have convergence. If this is bigger than 1, then we have divergence. And if this is equal 1, that's bad luck, because then you don't know. Meaning you shouldn't have used this test. Okay, let me give an example here how this works. It's a bit, that's why I'm saying you won't see it much, because it's a little bit contrived. Here is the example. So you notice that this is actually something here to the power n. And so that's the only case you want to use a root test, if you have the whole thing is a power of n, because then if you take the nth root, the power and the nth root will cancel. Okay, let's work that out. So if I would do this, I would have to calculate the limit for n going to infinity. I have to take the expression. Oh, by the way, sorry, I forgot to, very important thing, absolute values, because if I'm taking roots, if it's even roots, I cannot take even roots of negative numbers, so I have to take absolute value here. But you see, in many cases we are dealing with positive things, so I am not going to write the absolute values. Plus 6n plus 2 to the power n. That's my an, right? So this is an, just so that we know what you're talking about. And of this, I now have to take the absolute value. As I said, there's nothing there, and then take the square root. Okay, take the square root of the whole thing. And luckily, what happens is, of course, that the square root and the n power, the nth root and the nth root and the n power cancel each other out. So what we're left with is the limit for n going to infinity of just what is inside. 3n squared plus 5n squared plus 6n plus 2. And we have done many times this kind of limits now. You could do L'Hopital, but it's much easier to just divide top and bottom by the highest degree, which is n square here. So divide that by n square, n square, n square, n square. Do this step, please do this step, especially on quizzes, because sometimes people really get confused here and get the wrong numbers. It matters here. So we have a 3 plus 1 over n squared, and then we have a 5 plus 6 over n plus 2 over n squared. I hope you see this. And then, as always, if I plug in infinity in each of these reciprocals will go to 0. So what I'm left with is 3/5. Now what about this? Well, let's look. 3/5 is the good case. Yes, 3/5 is less than 1. I'm getting tired. So 3/5 is less than 1, so we get convergence. Okay? And you can do other ones like this. There will be more in the book, a few more in the homeworks. But as I said, it's really very special, and you're only going to do this when you have actually an end power, and then you can kill the end power with the end root. But the more important one is the ratio test. And let me remind you, two of the most important instances that we're going to use it is we get a mixture of polynomials and exponentials, so that we cannot compare to the p-series or to the geometric series. It's like a mixture of these two, and also factorials. If you have factorials, you're always going to have to use the root test, the ratio test. Okay, guys, do not forget to put a comment with your name that once you have watched the movie.